Now there is another operator over a language that is called what we call as clean closure. Here, do you people have you people gone through that? What is clean closure? If L is a regular language, that means I can have a finite state automata DFA, NFA or epsilon NFA to accept that language. Then on the other side, there always exists a regular expression with which I can generate the words of that language. Okay. Conversely, if I have a regular expression, I can always build a finite state automata of DFA, NFA or epsilon NFA to accept that language. So we can view it like this. Just a second. We can view this as a so there is a regular expression which is generating, which I can tell you that's a generator, generating strings of L, and that strings are getting accepted by a DFA, NFA or epsilon NFA, because all these are interrelated. Understood? Because given a if NFA, I can always create a DFA, and given a epsilon NFA, I can create a NFA. Okay. So this is two-way. So if I have a DFA NFA, I can get the strings of the language it accepts, and I can create a regular expression. And if I have a regular expression, I can generate the strings of a language, and I can create a DFA to accept those strings of a language. Okay. So this theorem, in order to prove this theorem, we need to prove it in a two-way fashion. First, if R is a regular expression, then can I create, then I can say, then there exists a epsilon NFA. Okay, let me write it as ENFA to accept LR. Okay, so if I can prove this, then the just no, nobody is there. Just a second. Now it is coming. Okay. So if R is a regular expression, okay, then there exists a epsilon NFA to accept LR, the language LR. So this represents the first way arrow. Okay. So this way arrow is represented by my first claim. Okay. And the second claim is, if there exists a DFA to accept a language L, then L can always be represented as a regular expression. So you must be knowing that every theorem that contains if and only if, you need to prove it in two ways. That is, if A, you have to prove B, and in the other way around, if B, you have to prove A in the discrete structure. Okay. So this theorem will be proved in two-way fashion. So let us start with the first way. So first I claim that if R is a regular expression, then we can always create an NFA, epsilon NFA, to accept LR. Okay? How will you do that? Can any guess how we do this thing? So regular expression is always so in the definition of regular expression, what R can be? First, let us start with inductively. So R is suppose phi. Then can you create an epsilon NFA for it? So what will be my epsilon NFA? My epsilon NFA will be like this way. This is my starting state and there is no finishing state. Means there is a finishing state but there is no transition between the starting state and the finishing state. Okay, so this represents an empty language because I am not accepting any language. Okay, similarly R is equal to epsilon, what it will be? That means it is a singleton language but it has no alphabet set. Okay, so what will be my equivalent epsilon NFA? My equivalent epsilon NFA will be like this. Understood? So from the definition of regular expression, I am gradually creating epsilon NFA, which is the theorem. Okay. Now suppose every alphabet set of A, suppose my alphabet set contains only A. Okay. Then what will be my so suppose my regular expression R is A. Okay. Then how will you create a epsilon NFA? So my epsilon NFA will be two states, one with starting state and with A it moves to the final state. Okay, understood? Okay, now let us come to the other parts. That is, given R and S, two regular expression, let R and S are two regular expressions. I am writing regular expression as capital R, capital E. Okay, let us not write it further. R and S are two regular expressions. Then, and they have suppose finite automatas. Suppose epsilon NFA. Suppose F finite automata 1 and finite automata 2. Okay. Then R plus S from the definition of regular expression is also regular. Also regular expression. So my question is, can I create an equivalent? What will be my equivalent epsilon NFA for it? Can someone tell me? So I have a regular expression R. That means I have a finite state automata for R, which starts with suppose QR. Okay, this is my starting state of QR. Okay, and this is my final state of FR. Okay, I represent the final state of automata that accepts the language of R as FR. Okay, now on the other side I have what I have just a second. On the other side I have a language like this way.